Today we're going to be discussing about the lower bound proof of elemental distinctness problem. So what exactly is an elemental distinctness problem? It's basically a problem that asks if all n elements within an array are distinct from each other. It's a decision problem. It will return a yes if true and a no if false. The lower bound for elemental distinctness problem is known to be omega of n log n. But how is this lower bound proven? Let's see. As you can see here, this is a decision tree model for a comparison-based sorting. As you can see here, we have an array with 3 elements, 1, 2, and 3. In order to find the lower bound of this decision tree model, we have to bound it to the height, which we know that the amount of max leaves are 2 to the h, and the minimum amount of leaves are n factorial. What does n factorial mean? N factorial means that at most, the amount of possible different arrays, like the amount of possible different sortings that can occur to this one single array, are based on n factorial, which is 3 factorial, right? Which then means that it's 3 times 2 times 1, which gives us 6. This means that there's 6 different permutations or 6 different random orders in which this array can exist, because it's based on 3 elements. So at most, the algorithm has to be able to solve at minimum, will have a minimum leaves of 6. As you can see, there's 1, 2, 3, 4, 5, 6, right? So if it's sorting is based in like is at this node, root node, we have A1 comparing to A2, and depending if it's greater than or less than 2, it will take the left side if it's less than or equal to, and then the right side if it's greater than. Then we know that the minimum leaves are n factorial, right? We discussed this earlier. So if we wanted to bound to the height, we need to solve for h on this one. So we know that by definition, the max amount of leaves you can have in any tree is 2 to the power of h, which is the height. So if we want to solve for h, we know that 2 to the power of h has to be greater than or equal to n factorial. So over here, we have log of 2h, and then is less than or equal to log of n factorial, which then gives us h is greater than or equal to n log n, which then tells us that base bounded by the height, at worst, the lower bound is omega of n log n for any comparison-based sorting based on the decision tree model. So this right here is important because as we know that if at minimum we need to have n factorial leaves, we automatically understand that omega of n log n is the time complexity for any algorithm that has to have a minimum of n factorial leaves. So let's press on. Right, so how are we going to prove the lower bound? So the main proof is insinuating that the time complexity is omega of n log n. We're also claiming that x is an array of numbers from x1 all the way to xn elements that are distinct from each other, right? And then we're saying that y is a non-trivial permutation of x, meaning that it has the same elements, exactly the same, just in a different permutation, a different order, a random non-trivial order. So then we're saying that we're also claiming that RL, which is the instance in which leaf L is reached at the end of the execution, therefore RL is connected. We're saying that the region in which L leaf relies on is a connected region, right? That's one of the third claim. The fourth claim is that when we're to solve for x, when we get the answer for x, we'll get an answer of yes on leaf L1. And then if we were to get an answer for y, we'll get another yes, but on a separate leaf of L2. And this is going to be important in proving the lower bound later on. So based on these claims, the amount of yes leaves have to be greater than or equal to, because remember there's 2, right? So it has to be in a different leaf. It has to be greater than or equal to n factorial. So then that means that the time complexity will give us omega of n log n. So what is connected versus convex region? So this is going to be important, but the definition is of a connected region is defined as any region, which is R, any region with any points that exist within any points x, y that exist within R, within this region in which any path exists from x to y passing entirely through R. A convex region is defined as any region with any points x and y within R within the region in which a straight line path from x to y passing entirely through R. Therefore, by definition, a convex region is a connected region. A convex region are easier to prove, and when you prove a convexity, you will also prove a connectivity. So what we're saying here, what is a connected region? So we'll look over here, right? So this is, I did a two-dimensional vector here, right? So this means that n equals 2, right? So at most, right? So that means it's comparing two elements. It means it has two elements in it. So at most, we know that the omega is n log n, right? Correct? So it'll be 2 times log of 2 factorial, which then gives us 2 times log of 2 because 2 factorial is just 2 times 1, which is 2, which then log of 2 is just 1, which then gives us 2 times 1, which just gives us 2. So that means that there will at least be 2 yes leaves. There has to be a minimum 2 yes leaves, right? So in a two-dimensional vector, you do have 2. This one is your L1 leaf and your second leaf here. So what's this vector right here, right? So then this vector separates the region of L1 and L2. So L2 is his own little region, right? It's an own little region over here. And L1 has his own little region over here, right? Within the boundaries, but it's separated by this vector, which means that when if so so since we have two elements, right? We have x, which is going to be xn 1 and x2, right? So there's two possibles, right? They're either going to be greater than, less than, or equal to. When they're equal to, we know that the answer is a no. So this vector right here is insinuating that the first and the second are equal, which then means no, which then separates the region. You can't cross L1 can't cross down to L2 and so forth. So therefore, this is his own separate region down here. L2 is his own separate region down here, and L1 is his own separate region. L1 region is when x is less than y, and L2 region, right, the leaf to yes, is when x is greater than y, right? So based on our complexity, time complexity, we've proven that even when you're in even a two-dimensional, you'll have two separate regions for leaf 1 and leaf 2. So let's press on after this. So we're going to prove this by contradiction, right? So we're going to keep the same claim that x is is an amount of x1, x2, x3 all the way to xn, and y is a permutation of x, the same concept, which means it has the same elements, just in a permutated order, meaning it's just a different random mixed up order. But then we're introducing this new z, which is they're going to have the same amount of elements, but ci equals lambda of xi plus 1 minus lambda yi for all i's. where lambda is any positive number between 0 and 1, where 0 is less than or equal to lambda, which is then less than or equal to 1. So z is on the straight line segment joining x and y. Example, the vector. So if we look back, z will fall in between these two regions, in its own region where the answer is no, right here, right? The answer is no. So, because if they're equal at any time, there's no, this is going to come important when we're when we're proving based on contradiction, right? So that being said, so now we're saying that also that R, the region of where leaf one is a convex, right? Because answer X will lead us to a yes answer on leaf one, answer Y will lead us to a yes answer on leaf one, and answer Z will also lead us to a yes answer on leaf one, right? So let's prove the first claim, right? The first claim is that R region of L1 is a convex, right? So executing a Vincent of X will land us on yes on leaf one, so would Y, and so would Z. First, they're both, all three of them, all the three answers are going to land us on a yes of the L1. So basically, we're assuming the X, Y, and Z will land us on this region right here. So now we're going to let the root label be a comparison of Y and J. So you remember in the beginning, we talked about the decision tree. This is considered the root label. So we're going to let it be a comparison of I and J. And then we're going to pretend that the less than path was selected based on the root label in execution 1, right? And then the execution 2 will also take the less than path because both reach leaf L1. So if you remember on the two-dimensional vector, right, leaf 1 rests whenever x is less than y, right? So since they took the, when x is less than y, since they took the less than, they will reach to L1 as a result. Right? So by insinuating, this insinuates that xi is less than xj and yi is less than yj, right? Now let's make the less than argument for z also, right? So this will be zi is lambda of xi plus 1 minus lambda of times yi is less than lambda of xj plus 1 minus lambda of yj, which then gives us zy is less than cj, right? Therefore, since c takes the same path as xy, we can conclude that z will also reach L1, therefore making region of leaf L1 a convex, right? So it is true. So if they're all in here in this region, and they all have direct paths to L1 and to each other, therefore it makes it a connected region, as we defined earlier, which makes it a convex, right? And by definition, all convex are connected regions, all right? So now we're going to prove the claim that the answers of x, y, and z all lead to yes on leaf 1. So x and y both reach the same leaf L1, right? Because R of L1 is a convex. Therefore, there's just a path from x to y that passes through leaf 1. Once again, remembering the definition of a convex. It's a direct path, right? A straight path. Then we will show that there's just a point z within the p path such as the answer of z is no. This is us introducing the contradiction. So in order to prove this, we're going to add a little subclaim here where there exists an I and j such as that xi is less than xj and yi is greater than yj. So we're going to define a function of fw where wi minus wj, right, equals, the function equals wi minus wi. Therefore, since xi is less than xj, when you subtract them, the function will always return an answer less than 0. And since yi is greater than yj, the function of fy will return a value greater than 0. Based on the mean value theorem, the C point in path P will exist such that the function of fc equals 0. And if the function of fz equals 0, we can insinuate that zi equals cy because you're subtracting them. In order to get 0, they both have to have the same value. Therefore, it's proven that answer C will equal no, this is a contradiction to our original claim of answer C giving us a yes. So if you look back, by contradiction, this is not true because the answer to this is no. Because if we look at the vortex, right, it means that it equals. There's going to be a point where it equals 0, which is going to give you the answer of no. If you look at the vector, yep. So now let's press on. So now we're going to continue. We're going to prove this subclaim too, right? So to prove this subclaim, I made a x with 4 random elements, 3, 6, 2, 7, and then I made y, which is a permutation of x, which is 6, 7, 2. So it has the same elements, just in a random order that I picked, non-trivial, in which then we have this function here of p that sorts x, which makes 2, 3, 6, and 7. Basically puts x in order. Since y is a permutation of x, it could never, if x is sorted, y can't be sorted. So how do I get these numbers down here for this p of y thing? So basically I go over here, I look at 2, right? And what's under 2? 2. So I bring it over here, 2. The next number is 3 for x. I look at 3, what's under 3 for y is 6. I bring the 6 over. I look at, right? Then the next number is 6. I look at 6. I got 7 down here. So put 7 here, 6 and 7. And then the last one, 7, 3, just stays where it's at. And that's 7, 3. That's how I got these values down here. Since y is a permutation of x, y could never be sorted if x is sorted. So at some point of y and j, y will take the path of greater than. So if you can see here, right, if we go to order, if at some point, if you look at this region right here, right, for x, 6 is less than 7. But for y, 7 is greater than 3. Meaning that we will reach a new leaf of L2. This is also another contradiction to our claim, which was insinuating that there's another contradiction that we will reach it. Y will answer yes on leaf L1, which is not true. It will be on L2, right? So that contradicts, that's the next contradiction. So in conclusion, since x will reach a different yes leaves than y, that means that at minimum, the total leaves have to be greater than or equal to n factorial. As proven earlier, the time complexity of a decision tree is omega log of n factorial, which equals omega of n log n. Therefore, by contradiction, we have proven that the elemental distance problem has a lower bound of omega of n log n. And thank you for listening. This will be the end.